Hey, remember this guy? Who doesn't love Waldo? But we're not here to ask the question, where's Waldo? What we're going to be asking as we go through this video is, where is the vertex? And he's just going to remind us of that. Because as you look at your notes, you see this chart. And in this chart, you're going to use this to help you decide how to approach a certain problem. But your question is always going to be right here, first of all. Ooh, nice highlighting, Mrs. Pryor. First question is always, where is the vertex? So you have to answer that before you can really move on and make a good decision about how to approach the problem. So let's walk through each one of these. We'll keep referring back to this chart as we go through several examples. First of all, when the vertex is at the center, what do we do? Well, we've actually answered this question in a previous lesson. We know that's called a central angle. And actually, I think I want to write that down. That's a central angle. And the measure is always equal to the arc, the angle equal the arc. Remember, if this, for example, this x here was, say, 20 degrees, then we would know the arc would be 20 degrees. They're always equal. There's enough said about that. Let's go to the next one. When the vertex is sitting on the circle, then what do we do? Well, we've seen an example of that also in a previous lesson. Here's a vertex on the circle, and we call this an inscribed angle, and it intercepts this arc across from it right here. And we've learned that this angle x is going to equal half of our arc. That's the relationship. That's an inscribed angle, but this other kind right here, this is new. It's called a tangent chord angle because this line here is a tangent and the other side of the angle is a chord. Pretty self-explanatory, but how does that change what we see? Let's go back to that demo that we saw in a previous lesson. You'll remember this. We dragged the angle around and we saw that the arc and the angle both changed, but they stayed in that 1/2 relationship. Well, I want to show you what happens. Let's extend those chords out to make them raise, and let's look at what happens when this point C comes closer and closer to point D. Notice, again, the angle doesn't change and neither does the arc. But when point C comes together with point D, then we get that tangent line. And so this arc is still the intercepted arc, and it still has that 1/2 relationship. So pretty cool. We have exactly the same formula we saw before. That's going to be your intercepted arc, the part of the circle that's contained inside the angle all the way down to this point of tangent C. And that angle is half the arc. So here's an example. We have this angle B that we're looking for, but we see this arc on the inside. That's 160 degrees. Our arc is always half the angle, so our angle would be half of the 160 degree arc that's contained inside of it, or 80 degrees, which is angle B. And there isn't any more to it than that. Here's another one. What's the measure of arc BCD? Be careful though, you got to read it right. BCD is this arc right here. So we have our 108 degree angle. Let's highlight the arc that intercepts. That comes from the point of tangent C all the way around till we hit B. And that arc is going to be 2 times the 108. So that's a 216 degree arc. It's not the one we want though. We want this one. This is just going to make up the rest of the circle. The total of 360, and we'll take away that 216 degree to see what we have left. So I'm looking at 144 degrees. Okay, let's go back to Waldo, who's going to ask us when the vertex is inside the circle. So looking back at our chart, if we're inside the circle, we're looking at this angle right here. The vertex is right here on the inside. And that's called a chord-chord angle because it's when two chords are intersecting. Now this is a little bit different because we see, actually we have two arcs involved here. This arc here, which is inside of our angle, and this arc over here, which is inside of the vertical angle. That angle there. Remember, vertical angles are congruent, and this is my own term. I call these vertical arcs. They're not congruent though, be careful. But look at our formula. It tells us to add those two arcs together, divide by 2, or take half of it. That sounds like an average to me. So to find angle x, we're going to average the arcs. Angle x would be 1/2 of the sum of arc 1 and arc 2 as a formula. So let's try that in an example. Our job is to find our angle x here. Let's identify the intercepted arcs. The first one's here at 70 degrees. The second one is opposite it in our circle right here at 50 degrees. So our question marked angle, if we just follow our formula, is going to be 1/2 of the two arcs added up, which are 70 degrees and 50 degrees. Okay, so tell me, what's half of 120? Final answer is 60 degrees for the angle. And of course, I have to throw some algebra at you. We're going to find the value of x here. Here we see an angle inside of the circle. And let's identify those intercepted arcs. The first one's right here, this 185 major arc. Second one is opposite it right here. for the vertical angle. We're going to average those. So if we follow our formula, our angle is 125 degrees. That needs to equal 1/2 of our arc total. One arc is 185. We're going to add that to our second arc of 8x plus 1. So here comes the algebra. Let's go ahead and simplify what's in the parentheses with some like terms. Let's put the 8x first, and then adding 185 with one more is 186. Those are both even. I think I'm going to go ahead and distribute that in. Half of 8x is, of course, 4x, and then half of 86 will be 93. Okay, you can do the rest of this algebra. I'm going to just kind of walk you through it, but I'm going to be quiet because I'm getting thirsty. You stop me if you see a mistake. Oh man, no, I'm stuck. 32, I hope. Okay, dividing by 4. X should be 8. Find the value of x, that's our question. That's our answer. Okay, our final one. This is when the vertex is sitting on the outside of the circle. And you see on our chart we have 3 different situations. Let's walk through each one. We have a secant situation. So our vertex is on the outside. That's true of all of these. But we have a secant line passing through. Both of these lines are secant lines. And you'll see again there's 2 arcs identified. Both of them are on the inside of the angle, which is important. Those are the 2 arcs we're going to be using. Sometimes I call it a far arc and a near arc. Near to the vertex and far away from the vertex. When you have this second example, you got a secant tangent line. This second line is just tangent here, but it still divides us into 2 arcs. We have this far arc that goes up to the point of tangency. And let me change color now. This interior arc right here that's closer to the vertex, those are actually just connected, but those are the 2 arcs you are going to use. I hope you can see those. And then this last one, this is pretty unique. When we have a tangent, and they're intersecting on the outside, our vertex again is on the outside. This divides our circle into 2 arcs. Split at the point of tangency. We again have our far arc here, arc number 1, and then the rest of the circle completes with the second arc right here. So we end up using the whole circle in this case. All of these are the same formula. Our vertex is on the outside. We are going to subtract our arcs. Notice that arc 1 is the one that's far away. It's the bigger arc always. And then we subtract from that the near one. That's to avoid any negatives, of course. So our angle x is equal to half of the difference between the arcs. Subtracting those arcs, let's calculate them with an example. Okay, vertex is on the outside of the circle. My formula is to subtract. So my angle, I'll use my angle x here, is 1/2 of arc 1 minus arc 2. And so let's look at where our arcs are. First arc 1 right here is on the outside far away. That's 145. And then secondly, my second arc is right here. So we're taking the pieces that are inside the circle always. And then that will give me the rest of my formula. So I just got to calculate this. So let's take 145 minus 55 first, which is, I believe, 90. And so half of 90 is 45. We got a 45-degree angle. Done. Here's another chance for us to practice this. Vertex on the outside. Always look for that. Let's find the arcs where this is intersecting. So first arc is this big arc TW right here. And then our second arc is on the inside of our angle. It stops at V right there. So this piece of the circle that's not inside the angle, I don't even use it. We're looking for the red arc, TW, the big one. So let's go again to our formula. Our formula is that the angle is half of the difference of the arcs. We're subtracting again. So this time we have our angle, 58. We can just plug that right in. But our arc 1 is what we don't know. Let's just leave it at arc 1 and subtract 89 for arc 2. Okay, so this is the kind where I think it's easier to multiply by 2 and clear out that 1/2. And then we just won't deal with the fraction at all. So we have arc 1 minus the 89. And over here, we're going to take 2 times 58, or 116. So last step, we're just going to add 89 on both sides. You know how to do the rest of this. Our final answer for our arc 1 is that total, or 205, I think. You better check my arithmetic there. Just adding those up. Okay, one more example, or no, 2 more examples for vertex outside the circle. Same deal this time. Here's the vertex. Let's see where our arcs are. These are from the point of tangent. See, we're going to use the whole circle in these cases. So big arc number 1 is 250. No idea really what arc number 2 is, or JL, or do I have an idea what that is? I'm going to need to know that because my unknown is down at the angle. So how can I get this arc right here? Maybe pause the video and think about that. I hope you noticed you got the whole circle. So my red arc should be what's left over from our 360 total after I take out the 250. So it should be 110. That's how I figured that out. Okay, we're ready to set this up. Let's give our angle, which is our expression, set that equal to half the difference of our arc. So I want to take half of 250 minus 110. Okay, let's simplify that a little bit. What's half of, let's see, 250 minus 110 would be 140, and half of 140 is 70. All right, you should be able to finish it from there. We're going to get 11x equals 66, and x is 6. I think that's what I was looking for. Okay, our final example, and I saved the best for last. This one's a little bit trickier. You're going to notice something kind of unique. We don't know any arc. We just have this circle, blank circle. All we have is one angle out here, 50 degrees. This is how they do space stuff. Imagine this is the Earth and this is a satellite or something orbiting Earth. Well, how do we figure out this missing arc, this VT arc? What you want to do is you want to take the near arc and you want to call it x. The nearer arc you want it to be x. The other arc out here, we don't know this one either. But what we do know is it makes the whole circle. So just like over here where we subtracted, remember over here we subtracted from 360? We're going to do the same thing right here. It's just going to look weird. We're going to take 360 minus x. And that's as good as we can label that for now. But that's going to help us set up an equation. So with our formula, we're going to take that 50 degrees as our angle, and it's going to equal half of the difference of our arcs. One of our arcs is the 360 minus x. That's our big one. And the other arc is the x. Okay, so we got them color-coded there for you. Remember, you want your near arc, your smaller one, that's usually best to call your x, your unknown, and the big one can be 360 minus x. And then it's just a matter of algebra. Don't you love it? Okay, so let's simplify what we've got. That's, of course, 360 minus 2x. And let's go ahead, this time these are even again, so I'm going to distribute that half in. And I'm looking at 180 minus x. So 50 is 180 minus x. Let's subtract the 180. And I'm running out of room real quickly here. Let me come over here. So I'm saying a negative 130 is the negative x. Okay, x is 130, guys. 130 for your final answer. That is up here. Let's go back to the picture, though. That's your little arc right here, 130. And you are done. Give the try these a shot. Remember, the question is always not where's Waldo, but where is the vertex? Have a good one.